And we are moving online with our next presentation, also part of the ZeoCat 3D project. We have connected Leon Rousseau. Few words until we finalize the connection. Currently, a PhD candidate in the Chemical Process Intensification Group at the Chemical Engineering and Chemistry Department of the Eindhoven University of Technology, Netherlands. His PhD is performed in the ZeoCat 3D Horizon 2020 project context. And during his research, he worked on 3D printed catalysts for chemical process intensification. In his presentation today, he will reach the topic of optimal geometries for 3D printed catalyst structures with focus result on the geometry of 3D printed log pile structures. And the results will be framed both in the context of methane dehydroaromatization and for other exemplary reaction systems. I will leave Leon continue his work. Leon, can you hear us well?
Yes, very well. I hope you can hear me too and see the screen as well.
Perfect. I will pass the microphone to you.
Perfect. Thank you very much for the kind introduction and of course for organizing as well. So today indeed I'll be telling a bit about our research. We also did it in collaboration, of course, with Vito, with hybrid catalysis and with 3D Cut as well. So a big thank you to them already from the start. And as mentioned, I work in process intensification. And the idea of process intensification is actually super, super simple. What we want is a process that uses less energy and uses less feedstock to get the same amount of product. Therefore, it has a higher efficiency. Ideally, we would like to get less byproducts than in a normal process. And if we can ask for anything more, then also to get a smaller plant altogether would be very, very nice. These are the goals of the process intensification. And anyone could think of these goals, of course. It seems obvious. So the goal is very clear, but the way to get there is a whole different story. So things we commonly do to achieve these goals is to increase the heat and mass transfer. Now, a chemical reactor is often just a tube. So reactants, often gases, come in from the bottom. They react and then they either use or produce heat. And the walls of this tube is then either hot or cold to extract this heat that's produced or used by the reaction, because we want to attain an optimal temperature. And the better we can approach this optimal temperature, the better the reaction will go. So increasing this heat transfer and also the mass transfer is one of the main goals that we try to achieve. Then the second one is to integrate the reaction and separation. So what often happens is that we do a reaction in one vessel and you make a lot of byproducts. And the problem is then after that, we need a lot of different vessels again to separate those byproducts out. And that, yeah, you both need all the vessels and it costs a lot to operate as well. So again, not ideal, and something by integrating those reaction and separation steps, we can really make a better process altogether. And the final one is forced periodic operation. So we have already heard about catalyst deactivation today, and what we can do is not feed the same gas mixture to a reactor 24/7, 365 days a year, but sometimes switch the gas mixture to either manage the heat better or to regenerate the catalyst. And in any case, make for more optimal operation. And today we'll be looking specifically at that heat and mass transfer. One of the more basic ways to influence this is by what is inside of this reactor. So as I mentioned, it's a tube and inside is catalyst, because catalyst is what makes the reaction happen. And the geometry of this catalyst and the way that it's packed in the reactor really influences everything that happens. So as I mentioned, only the walls are hot and the gas is everywhere. So being able to have that gas contact the walls as much as possible is critical to having good heat transfer and the temperature that we want everywhere in the reactor. So the catalyst geometry and the packing, the way that it's laid about, tells us how the gas will flow around and how much it will contact the wall. So this is super critical in ensuring the good heat transfer. Of course, if you really block all the gas flow, there will be a lot of pressure drop as well. So this is often the counterpart of the optimization that we have. And then there's also the resonance time distribution that we influence, and the size of the particles especially influences the internal diffusion limitations. Now, there are two main categories that we see in industry nowadays, and the first is the randomly packed beds. So you have either spheres or like these pellets that you see above here, and we just throw them in a big reactor. It's super dense, so a lot of catalytic material per volume of reactor, but the pressure drop is relatively high, and the heat transfer is not amazingly good. Then the other end, we have the cellular structures. So you see them below here, very open structures. So the pressure drop is low. Often these structures have a backbone of metal or of a very conductive ceramic. So the heat transfer is very good. But because the catalyst is then coated on this inert support, the holdup is very low. What we are then looking at is the 3D printing of catalysts. So this is something new, a new way to shape catalysts. And I'm going to start us off with a disclaimer that the 3D printing is fairly complex and relatively expensive. So 3D printing is commonly in use for about a decade now. Everyone can have a 3D printer in their house. But 3D printing catalyst is really a whole different story, because it's a ceramic, and it's a ceramic that we cannot sinter, because then we lose a lot of the properties. So we mix this catalyst powder with binder materials with some liquid to get a paste. And then using the micro extrusion technology, which Vito is using mostly, we press it out through a sort of syringe, and we draw a pattern basically, which becomes our structure. Then we need to dry that and to heat it, but we cannot make it too hot because we need to maintain all of the catalytic properties. It cannot sinter too much, so the porosity should remain the same. And of course, if we make a structure, we want it to fit exactly in our reactor. So to have the intended dimensions, taking into account some shrinkage sometimes, but also the mechanical stability. So to ensure that we have a stable structure which will not break instantly when you touch it is very important. And like you already saw in the previous drawing, what we mostly produce are log pile structures. And the name comes actually from when you stack logs or pieces of wood, you stack them like this on top of each other, and you get a half open structure. This looks a bit like a monolith that we saw in one of the previous pictures. But in a monolith, you really have channels with walls on all sides. And here you have some openings. So what we see, this is the top view of some structures. This is the side view. So in principle, the gas would travel upwards and could also choose to go to the side, which is of course better for the heat transfer, as I mentioned. And then we can change how we stack and how we space the different parts of the structure to get different variations. And the porosity is between 40 and 60%. Sometimes 70%, which is in the middle of what we just saw. So just to recap a bit, we have these very open structures on the left-hand side of the graph here, low pressure drop, low catalyst holdup. And then on the other end, we have the very dense structure, so a lot of catalyst, but also a lot of pressure drop. And in the middle, we could have this additive manufacturing technology. And hopefully we can play around a bit with some parameters to get some more interesting pressure drop and heat transfer results. Now, of course, we did this. We took one of these log pile structures and we wanted to see how the gas moves through it. And this is called the transverse dispersion. So basically the rate at which gas moves through the site. And again, because the site is often heated, it's important that we have this rate as high as possible. It's very difficult because most gases you cannot see, and the gases that you can see, they are either very toxic or very exotic. So we don't want to use those straight away. And that's why we used an infrared absorbing gas and an infrared camera to visualize this gas. And you can see on the small computer screen here on the side that the gas enters in quite a narrow bundle and exits a bit wider. And the broadening we can correlate to the mixing phenomena within the reactor. The good news is that these structures that I showed you before, we can provide some variations in this transverse dispersion behavior. So you see here 5 different structures, and what we do is place them further and further apart. So the dark blue, we have the cylinders relatively close together. Then the red, they are a bit farther apart. And then the purplish color, it's even further apart, so the porosity increases. And the graph is, I won't go into every detail, but you can see on a global level that if we increase this porosity, the transverse dispersion decreases. So we can play around with this as a variable. So this on its own is quite a nice result, but in the context of this process intensification, it's not all that good. Because if we look at what a normal packed bed of spheres provides, it's actually higher than all of these values. So we do have some transverse dispersion and some flexibility, which is not there in a packed bed. But the overall values within which we can change, they are quite low. And again, I want you to take into account that 3D printing is not so easy, can be quite expensive. So we really need to think, is this the most optimal use of the technology? And of course, we think it's not. It would be sad to end the presentation on that note. So we have looked a bit further on what could you do with this micro extrusion technology, direct ink writing, to make structures that do a bit better. And one of the unique advantages of 3D printing, we think, is to include local variations in a structure. This is something that is nearly impossible to do with the conventional methods of shaping, but 3D printing can do it relatively easily. So you can see on the picture, this is a plastic structure, not the actual catalyst. So we have a sort of grid-like structure, just like the log pile, but in some places we add an extra cylinder. And in this way, we make a baffle-like structure. So it's a denser zone, so the gas is less likely to go through that. It would like to go around that. So we would have here that the gas goes around it and goes inward, goes around it and inward. And getting this swirly flow, this cross flow, would really enhance the contact with the wall. And the nice thing is that because it's open, it's not a fully dense structure, the gas can also travel through it, so the pressure drop will be not as high as it normally is. But of course, making a structure like this, you have a really wide range of design variables to tune. And I won't go into all of them, but what we found was that the baffle length should be rather high. So the baffles need to run almost through the wall. So they need to deliver the gas very close to the wall. And then how dense the baffle really is, so the spacing of those cylinders, we can use as a tuning variable. And I have some small videos to show what I mean by that. So here we have a same structure from left to right, going from a more open structure, so high spacing to low spacing. And we inject a tracer gas, and then we see how that tracer gas moves through the structure. On the left-hand side, so again, the more open structure, you see that some of the gas travels along the wall, but we also get a very big cloud of gas just bypassing through the middle. And of course, this gas is not in contact with the wall, so it doesn't exchange heat so well. So it doesn't fulfill our purpose to the greatest degree. Then in the middle, the spacing is a bit lower. Everything is closer together. You can see that we do a bit better already, but especially on the side, we have an even lower spacing. You can really see that we have a plug of gas moving from left to right, hitting the wall alternatingly. And of course, this is good for the heat transfer, but will also be paid for in pressure drop. And this is what we specifically looked at. And again, I will spare you all of the details, but it's nice to show one example where we performed some different experiments for one structure. So we vary the velocity at which the gas comes in. And then we look at what is the pressure drop of the structure relative to what a packed bed would have. And this we see in the top graph. So for almost all of the velocities, we see a pressure drop, a relative pressure drop of approximately 0.2 or 0.3, which means that we need 20 to 30% of the pressure drop only compared to a packed bed. So it's, in terms of pressure drop, much better than the packed bed. And in terms of heat transfer, which is here quantified by the Nusselt number, we have an even better result because the heat transfer is 8 to 4 times better than a packed bed. It decreases a lot as function of the velocity because it's the higher the velocity, the more bypassing through the center of the structure we have. So that's not ideal, but I think the picture is quite clear. So 4 times as low pressure drop and 4 to 8 times as high heat transfer, which is of course very promising. And with these conclusions, we are also thinking about what to do next, because these are, of course, computer simulations. We want to show it in real life. And here I again come back to my disclaimer about how difficult it is to do this in real life. On the right-hand side, you see one of the structures provided by Vito. And first of all, I should mention that these are still relatively brittle structures. This one is in fairly good shape, but you can see some of the dust formation on the side where it has broken a bit. And of course, we need to put it inside of a reactor, so it needs to be quite stable. But what the real bottleneck here is the dimensional accuracy and the wall coupling. So we saw before that we can make the gas really swirl from side to side within the structure. But as you can see, the structure has its own small wall on the side, which acts as a heat transfer barrier. And especially if this wall doesn't perfectly touch the metal reactor wall that we use in the lab, the heat transfer is not so optimal. So this is something that is really, really difficult to optimize. And the second thing is maybe not so straightforward, but to find a fitting test reaction that we can actually do in our labs, because a lot of reactions have heat transfer problems in industry where you have meter-sized reactions with tens of centimeters of width. But in the lab, in our lab at least, we are using centimeter-sized reactors. So it's sometimes a bit harder to prove these sort of things. And therefore, we need a very highly endo or exothermic reaction, which has a very significant equilibrium shift as a function of this temperature. So the reaction produces or consumes heat and therefore slows itself down. We want to really see that effect in our lab. And we want to make sure that the heat or mass transfer limitations are the main issue in this reaction, in the implementation of this reaction in real life. So we looked at some different reaction systems. The first is the methane dehydroaromatization, of course, the reaction of the ZeoCat 3D project. And this has proven to be fairly difficult. Because it's such a complex reaction network, you have many products, and because there's such a rapid deactivation, it is very difficult to perform a clear experiment from which we can say, this is better and this is not. And what doesn't help is that although the benzene formation reaction is very endothermic, the naphthalene formation is even more endothermic. So when we make for better heat transfer, we will actually boost the naphthalene production more than the benzene production, probably. Something we looked at in collaboration with hybrid catalysis has been the CO2 hydrogenation to dimethyl ether. But one of the problems, especially when modeling this reaction system, is that you have the methanol formation and the reverse water gas shift reaction, and they have opposite heat effects. And in a lot of our situations, they don't cancel each other out, but because they contradict, the overall heat effect is not as high. And therefore, the amount of performance increase by better heat transfer, we could not really make a really big impact with our 3D printed structure. Also in the literature, we really see that sorption enhanced processes are more the process intensification route that we are willing to go. So we abandoned that route for now. And finally, what we are working now is the steam methane reforming. Bit of an older reaction, but it has very, very strong heat effects. So we are talking 200 to 300 degrees temperature drop over just a few centimeters of reaction. And also the equilibrium very significantly shifts the other way when these heat effects take place. So what I've been wanting to show you with this is that we have a very nice technology. And when we couple it with an optimized design, we can have something that's really worth it in terms of process intensification, but that it should never, never, never be used as a one-size-fits-all conclusion. So really have a look at the reaction systems that there are, and if it is logical to apply the solution to that reaction system, because doesn't make sense to use it in every industrial context that we can find, in my opinion, at least. So that was the presentation from my side. I hope you find it interesting, and I'll be happy to take any questions.
Thank you for your presentation. We do have a set of questions. And
of course.
I will start with the one on your slide 12. When visualizing the flow, the question would be, all the structures have the same pressure drop?
No, not at all. Not at all, actually. The difference is a factor 4. So what is interesting about these structures is that a lot of people ask me, what is now the best structure that you can make? But what is for me interesting is that you get heat transfer at the cost of pressure drop. So for some industrial processes, heat transfer is super important. So you should really, really push that. And it doesn't really matter how much pressure drop you get. For other processes, maybe the pressure drop imposes so much cost on the OPEX that is the main variable. So what we've tried is to really map out how do the heat transfer, the pressure drop and the geometry correlate, so that when you have an industrial challenge, a reaction system with certain effects, how can I use what structure to combat those effects? That's the main thing we have been looking at.
Thank you. I will move to the following question. When would you expect commercial efforts in this area?
That's an excellent question, especially because there are already commercial efforts. I know BASF has commercialized the technology last year, but they are quite, they don't tell a lot in their press releases. So we don't really know what the main advantage is that they are pushing. But from my side, especially the structures that we are developing now, I think what should be focused on is now more modular reactor types. So rather than, let's say, replacing the meter-sized columns that we have in the large refinery systems, we make smaller modular systems, for example, for local hydrogen production in the case of the steamer forming, or any other reaction. One of the classic ones is where they produce fertilizer on a farm, for example. So instead of needing a very big reactor, you make an optimized structure for a specific purpose and then produce on demand on site with that structure. So for me, that's where commercialization should be. And it depends a bit on the printing as well when we can come there. But I think developments are going quite fast because, of course, the 3D printing of catalysts has been published about for the first time 20 to 15 years ago, which in the research context is not extremely long yet. So I would say another time period like that, and we should see quite some significant developments already.
Thank you. I will then move to the third question we have for you. Are there any other structure designs that you are considering?
Yeah, it's a very good question, because the thing is that for 3D printing, a lot of people, they portray it as the sky is the limit. With a 3D printer, you can make anything that you could think of. For me, it was actually quite good that with the direct ink writing, the micro extrusion that we are using, you are limited in a sense to what the printer can do. Because, yeah, at some point you can think of everything. But for me, those designs, what we have done now is have these local variations, so these baffles along the reactor in the same way. What you could also do is change them over the reactor length. So what normally a reactor looks like is, in the beginning, you have a lot of heat effect, so a temperature spike, and that wears off over the reactor length. So you could argue, in the beginning, I need very good heat transfer with some pressure drop, and at the end, I need less of that. So that as a function of reactor length, you start changing the parameters of your structure. That for me would be the next step in topology optimization.
Thank you for sharing your knowledge, and these were all the questions that we received on the topic today. We have actually here one from the room. We have one question.
Hi, I'm Cristina from Lurederra Technology Center. It was really interesting, the information about all these advantages in the morphology part. And I was curious about the ceramic materials that are being used in the fabrication. What's your opinion, according to your background and long experience in this area? How deep has been gone the technology up to now regarding the compositions of the ceramic materials?
So I think if we scan the literature, most of the catalytic supports have been tried. So silica, alumina, silicon carbide, those structures. The problem is a bit that for every structure we try, you need to restart the optimization of your printer. So the catalyst base that you make needs to have appropriate viscosity and all sorts of other parameters, which basically means you need to start again every time that you do your reaction. And that's why it's fairly interesting what we did also all together in the ZeoCut project, because it would be fairly nice if you print standard structures, so just standard alumina, silica without metal doping, and then after the printing, put the metal in, or functionalize it in a specific way so that we can keep the printing part very generic. And then you can cater to all sorts of reaction systems, for example, and then the more specific chemical part comes after that. That for me would be a nice development, because I feel that we are still a bit stuck in that sense. If you read the literature, we still have to optimize every new material we do, which is not ideal, of course, for commercialization of a technology that you would apply to more than one process.
Okay, thank you very much.
We thank our audience for the questions, and again to you.
Yes, thank you as well.
Sharing.